Okay, can you see the screen? Yes. Okay, so today what we will do, so as I mentioned in the first lecture, that supersymmetry is useful in solving for solving some Hamiltonian systems. So we will see how this happens today. Okay, so let's consider a Hamiltonian H. Hamiltonian, let me call it H1. You will know why. Let me consider Hamiltonian H1, which is given by minus h cross square by 2m d by dx, d square by dx square plus v1 of x, where v1 is some potential. Now I want to solve the system. So what I mean by solving this system is finding all energy eigenvalues and corresponding wave functions, corresponding eigenstates. So this I mean when I say that I want to solve this system. Given a Hamiltonian, I want to find its energy eigenvalues and the corresponding eigenstates. So let's see how supersymmetry can be useful in solving a general Hamiltonian problem. So this, for now, V1 is a general potential. So let's say that let's factorize this Hamiltonian. So I write my H1 as some A dagger times A, where A is given by this h cross by square root 2m d by dx plus w of x, and then A dagger becomes, so dagger of d by dx is minus d by dx. I think most of you will know. If you have not, if you don't know this, this is as an exercise, just try to prove this. You have to use integration by parts. You have to apply it on a wave function, do integration by parts. Just try to prove it. It's a good exercise to do. Okay, so because of that, the A dagger becomes this plus w of x. Now, if A and A dagger are this, what is my Hamiltonian H1? So H1 is basically minus h cross by square root 2m d by dx plus w of x. The potential, this w of x is real, so the dagger is just w of x. H cross by square root 2m d by dx plus w of x. So let me say that, let me see if I apply it on some wave function psi, what I get. So the first term will give me h square by 2m d square by dx square on this wave function psi, plus I will get, if I multiply, minus h cross by square root 2m, sorry, minus h cross by square root 2m d by dx. Now d by dx is acting on, so this d, when this term multiplies this d by dx is acting on both w of x and on psi. I'm doing this like slowly because, yeah, it's the first computation I'm doing, so I'm doing it slowly. Plus, when this term multiplies this, it's w of x h cross by square root 2m d by dx on psi plus w of square of x on psi. Now the second term, this I use the product rule. I get h cross by 2m d by dx of w of x, psi is there, minus h cross by 2m square root 2m w of x as it is d by dx of psi of x, psi. So this term and this term cancels. So finally you get the Hamiltonian to be h1 is basically h cross square by 2m d square by dx square plus, sorry, minus h cross by square root 2m w prime of x, where w prime means d by dx. So this is d by dx of w of x plus w square of x. So this is the Hamiltonian. Now if I compare this Hamiltonian with the Hamiltonian I have taken originally, if I compare it with this Hamiltonian, I read off. So this is the kinetic term. So the rest of the term, this is my potential V1. So my potential V1 of x is minus h cross by square root 2m w prime of x plus w square of x. So what I have done, I have rewritten the original Hamiltonian in terms of some operators A and A dagger, and then my potential is given by this. And this W of x is known as superpotential. Superpotential. Okay. Now let's construct a supersymmetric system. Let's construct a supersymmetric system. So what I mean by constructing a supersymmetric system, I had a Hamiltonian H1 already. Let me construct a Hamiltonian H2 such that both these Hamiltonians H1 and H2 together form a supersymmetric system. So my H2 I define is as A dagger. Notice H1 was A dagger A. I define H2 as A dagger. If you plug in A and A dagger, you will find that the H2 is given by, if I write H2 as minus h square by 2m d square by dx square plus some other potential V2 of x. If you write H2 as this, you plug in A and A dagger, you will find that V2 of x is given by h cross by 2m square root 2m w prime of x plus w square of x. So there is this minus sign difference between V1 and V2. So H1 and H2, so my claim is that H1 and H2 together form a supersymmetric system. What do you mean by supersymmetric system? I'm giving this as an exercise. So check if I define H as some Hamiltonian as H1, H2, this matrix, and then I define Q as 0, A, 0, 0, and Q dagger as 0, A dagger, 0, 0. Check that this system obeys SUSY algebra. The system obeys SUSY algebra. That is H comma Q commute. Q dagger commutator gives you H, and Q commute, and Q dagger commute. Check this as an exercise. Okay. Now you can ask that given a potential V1, so my original goal was to solve for this Hamiltonian H1. And now what I did, I rewrote it in a way in terms of the superpotential, and then I defined another Hamiltonian H2. And now the point is, what I will show that both Hamiltonians, both H1 and H2, the spectrum of both H1 and H2 is related. So what I will show now is show the spectrum of H1 and H2 are related. So what I will gain by showing this? So if the spectrum of H1 and H2 are related, let's say I had to solve for Hamiltonian H1, I have to solve this system, but the potential was very difficult potential to solve. What I can do, I can find another Hamiltonian H2, maybe whose potential is easy to solve. Maybe this is easy to solve. This is not always the case, but sometimes this happens. So if this H2 is easy to solve, what I will do, I will solve for H2, and by solving just for H2, I can find energy states of H1, which was a difficult problem to do. So this is how supersymmetry will help you in finding the spectrum of the Hamiltonian H1. Another thing that sometimes happens that H1 and H2 are related to same physical system. So this will happen in the case of hydrogen atom, and I'll give you that example. So what will happen that H1 and H2 are related to different L quantum numbers of the same Hamiltonian. Hence, you can relate different energy states or different eigenstates at different levels to each other, and then you can use that procedure iteratively to solve for the Hamiltonian. So this is how supersymmetry will help you. So you found another partner Hamiltonian H2, which either gives you a relation between the energy levels at different eigenvalues, or which the other Hamiltonian is easy to solve, and then you can use it to solve for the original problem. I will show this explicitly. So let me. And the second thing you can ask, okay, this is how the H1 and H2 will help you. But you can ask that is it always possible to find such W of x? No. So if I am given a potential V1 of x, is it always possible to find a superpotential W of x such that I can do this procedure? The answer is, and how to guess and how to find this W of x. Because in terms of V, V is a complicated function. If you know the potential V, solving for W of x is not in general easy. So is it how to find W of x, or is it just a guesswork? So the answer is that if you know the ground state of the original Hamiltonian, you can find W of x. So for any generic potential, you can define W of x, and if you know the ground state, you can find W of x. Let me show how this happens. Let me assume for a moment that ground state of H1 has zero energy. So if it has zero energy, so H1 was A dagger A. So if the ground state, let me call it psi ground state, has zero energy, this implies that A acting on psi ground state of the ground state of the first one, psi ground state, is zero. Now A in terms of the superpotential, what was it? It was given by a differential operator. So H cross by square root 2m d by dx plus W of x acting on psi 1 ground state 0. You can just solve this differential equation. You can find W of x is just minus h cross by 2m, the derivative d by dx of the psi 1 of ground state divided by psi 1 of ground state. So W of x is just given by this. So given the ground state wave function, you can construct the potential W of x, and given W of x, you can do this procedure and find the corresponding supersymmetric Hamiltonian H2. So this procedure will work even if the ground state has non-zero energy. I can give that an exercise. So if ground state energy is non-zero, so if ground state energy is non-zero, what you can do, you can define your Hamiltonian H1 as A dagger A minus the ground state energy, and using that find W of x. Okay, so till now what we have done, so we had a Hamiltonian with a potential, and what we did, we wrote that Hamiltonian in a nicer way in terms of the operators A dagger and A. and then we found the corresponding supersymmetric Hamiltonian H2, which we define as AA dagger. Now the claim is that the eigen values, the eigenstates of both the Hamiltonian, the spectra of both the Hamiltonians H1 and H2 are related to each other. And using that relation, you can solve for systems. You can use supersymmetry to solve for systems. So let me first show how the spectrums of these two systems are related. Okay. So let's assume, let's say that some phi n of 1. So this is my notation. 1 means for the H1 Hamiltonian, n is the nth energy level. So this is the nth energy state of Hamiltonian H1. So let me say this is the eigenfunction of H1 with energy En of 1. It has energy En under the first Hamiltonian. So what I mean by saying this, that H1 acting on phi n1 gives you En1 times phi n1. Now you can check. Now we see that A acting on phi n1 is eigenstate of H2 with same energy. So let me check. So H2 acting on A times phi n1. What does it get? What is H2? H2 is A times A dagger, no? H1 was A dagger and A dagger A. H2 is A times A dagger. A acting on phi n1. This thing is just H1. So this is A on H1 acting on phi n1. Which H1 phi n1 was the eigenstate of H1 already. So H1 acting on phi n1 will give me En1 of A acting on phi n1. So this equation H2 of A phi n1 tells you that this phi n1, A times phi n1 is eigen state of H2 with eigenvalue En1. Is it clear? Okay. So and similarly, so this you can again do it as an exercise. So similarly, one can show that if phi n2 is eigenstate of H2, then A dagger times phi n2 is eigenstate of H1. This you can prove. So what I have shown, this is very similar to what we were doing yesterday when we were saying that fermions and bosons are paired. So this is very similar. So what I have shown, that the eigenstates of H1 and H2 are paired. That is, if and this happens for any non-zero energy. This doesn't work for the zero energy state. Let's say phi 0 of 1 was zero energy state. Of H1. Then H1 acting on phi 0, 1 is 0. This implies A dagger A acting on phi 0, 1 is 0. So A times phi 0, 1 is 0. But A times phi 0, 1 should have been the eigenstate of H2. But this term is 0. So you don't know if there is a corresponding. So you don't have a corresponding. So you don't have a corresponding eigenstate for H2. This is exactly same as the argument I was telling for fermions and bosons being paired for zero energy state. and unpaired for non sorry, unpaired for zero energy states and paired for zero energy state. No, okay. I think I okay. So what I have shown that the spectrum of both Hamiltonians H1 and H2 are related to each other. So if you can solve for one Hamiltonian, you can find the eigenstates of the other Hamiltonian. And this pairing doesn't happen only for the zero energy state. Okay. Any questions till now? You can unmute yourself and ask if. Okay. Okay. Let me now I will so now I am making another statement, that is, so the claim is that if one of the Hamiltonians so either H1 or H2 has a normalizable zero energy state, then the other one will not. So I already said that the zero energy states are not paired. Now I am making another statement, another claim, which is a stronger claim, which says that if one of them has a zero energy state, the other one will not have a zero energy state. Okay. Now let me try to prove it. So let's assume only H1. Sorry. Let's assume phi 01 is zero energy state of H1. Here this normalizable is important. So it's zero energy state of H1. So what I mean is that H1 on phi 01 is 0, or A acting on phi 01 is 0. And what was A? A was D by, okay, I am putting H cross equal to 2m is equals to 1. I don't want to, yeah. D by dx of phi 01 plus W of x of phi 01 is equals to 0. And you can now solve for phi 01. So phi 01 from here you will get is exponential minus some phi 01 at x 0 to x dy of W of y. This you can solve. Okay. Now if phi 01 is normalizable, what does it mean? This implies that the integral over dx of mod of phi 01 mod square from minus infinity to infinity is less than infinity. So it's bounded. So this is the definition of normalizability, no? That the mod that the norm is less than is finite. Usually you put norm to be 1, so you use the norm, you normalize it accordingly. But if it's finite, you can always set the norm to be 1. And now what will this mean? This, so since the x is integrated over minus infinity, this means that this, sorry, any question? Okay. Okay. So now, so this means,
You can ask the question to her.
Okay, my question is, this formalism is only true for supersymmetric systems or for any generic systems that we can do?
yeah, this is true for any generic system. Here I didn't assume anything about the Hamiltonian. So this is any general Hamiltonian H.
Okay.
Any general Hamiltonian. So given a general Hamiltonian, you can always find H2. But then whether finding H2 is a useful exercise or not depends on what H2 is. So you can, so given a Hamiltonian, you can always find the corresponding super partner Hamiltonian H2. But whether that finding that H2 is useful to solve problems or not depends on the form of H2. If H2 is as complicated as H1, you have not gained anything. Because what I'm trying to say that instead of solving for H1, you can solve for H2 and find the eigenstates, and hence you can solve a complicated problem in a simpler way. But if H2 is also complicated, or H1 and H2 are related to different physical systems, then it's not useful exercise to do. But you can always find a corresponding H2. So for any generic Hamiltonian. Here I
Okay,
haven't.
so how do we choose our H2 or that you have written like let's factorize the Hamiltonian as A dagger and
Hmm.
A. So
Yes.
this is because only you are taking the supersymmetric type Hamiltonian, isn't it?
No, no, no. You can always write. You can write any Hamiltonian in this way,
Okay.
because if you write it in this way, you will find that the potential should have this form. And potential is a
Okay.
local function. You can, so now this the problem. So given a potential, given some function of x, how will you separate that function in terms of w of x such that this you will get potential to be this, is a difficult problem. But as I showed, if you know the ground state, then you can find w of x using the ground state.
Okay. Okay.
So you can always find the yeah, finding this w of x is a difficult problem. But if you know the ground state, you can find that corresponding w of x.
Okay. Thank you.
Okay.
So,
Yes.
Diksha,
Yes.
so to solve this system, so you need to know uh, um, you need to know the ground state also.
Yes. If you sometimes you can just guess the superpotential w of x. Uh, if
Okay.
you can guess it and then it's fine. But most of the times, given a complicated potential, you don't know how to guess it. So you need to know the ground state. Then you can find it.
Yeah. Then I'm just can you go to the last line of your.
Yes. Yes.
Then
Only
this,
one.
yeah. Then this equation, don't you use the third last equation? Don't you use to find Wx?
Yeah, yeah. No, this I am just okay. This I am just showing here that given a w of x, this will say that only one of them has a zero energy state, normalizable zero energy state. I'm not finding the ground state using w of x. I'm just proving the other statement that given a w of x, only one of them will have a zero energy ground state. Both of them will have ground states, but zero energy will only be true only for one of the Hamiltonians. This is just a proof. When I will find the eigenstates, I will not use w of x in this way, because this is again instead of solving a differential equation which was second order for the Hamiltonian. If I had to solve directly for the Hamiltonian, it's a second order equation.
Yeah.
And here I am solving a first order equation. It's like a BPS, like the BPS equations that you solve in supersymmetry.
Right.
So you made the computation simpler if you know w of x. But then the question is like, again the question is how to know w of x. Either you can guess it, or if you know one of these phi's already, then you can construct w of x.
Okay.
Okay. Any other questions?
Ma'am, if H1 has supersymmetry in it, does this all thing really work? If H1 is by itself is a supersymmetric system.
So if H1 is by itself supersymmetric, then that Hamiltonian is anyway easier to solve, because then all of this will work. Then so you can take this capital H that I defined as your original Hamiltonian. Then what it will say, it will relate the different eigenstates of the same Hamiltonian to each other.
Right. And then the H2 will be, I can take H2 to 1. I don't have to really take to anything as H2 because
No,
my H1 is by.
no, H2 cannot be 1. If given.
It has to be 10.
Yeah, it will be it's like like in the symmetric harmonic oscillator. The supersymmetric harmonic oscillator was a supersymmetric system, but you could have decomposed its Hamiltonian in this way, where H1 was the bosonic Hamiltonian of the bosonic harmonic oscillator, and H2 was the Hamiltonian of the fermionic harmonic oscillator.
Okay.
And then you basically relate this, the relating the eigenfunctions of H1 and H2 is equivalent to saying what I was saying yesterday, that you relate the bosonic wave functions to the fermionic one. And there is, corresponding to every bosonic wave function, you have the corresponding fermionic wave function at the same energy. Those are the same that I'm making, that H1 and H2. Sorry, I'm using a bad notation here. H1 and H2, I was writing H1, H2. Yeah. Okay. Any other? Is it clear?
Yes, sir.
Okay. Any other? Okay. So now I'm assuming that phi naught mod square, so phi naught is normalizable. This means that phi naught mod square should be less than infinity. Since I am integrating from minus infinity to infinity, this means that at x goes to plus minus infinity, phi naught of 1 should go to 0, should fall off as x goes to plus minus infinity, because of the limits of integration. And then if that is the case, this will imply that your w of y, because it's an exponential of minus, there is a minus sign here, so this will imply that w, the potential x, should grow, because if it becomes infinity at x goes to infinity, then exponential of minus infinity is 0, so phi will go to 0. So should either grow or stay or fall very slowly at x goes to plus minus infinity. So you get a condition that w should be growing. And now if that is the case, now let's say that the Hamiltonian H2 also had a zero energy state. Let me call it phi 02. So if phi 02 was the zero energy state, then H2 acting on phi 02 was 0. This will say A dagger acting on phi 02 is 0, because H2 is A dagger. And this will give me, so A dagger is basically minus d by dx plus w. There's a minus sign here, no? Plus w of x times phi 02. This will give me phi 02 is exponential, but now you will get a plus sign here, because from 0 to some x, phi 02 of x, dy of w of x, w of I. So now if phi 01 was normalizable, then w was growing with x. But if w is growing with x, because there is no minus sign here, phi 02 is also growing. So phi 02, this implies phi 02 will not be normalizable. Hence only one of the Hamiltonians can have normalizable zero energy state. Is this argument clear? Okay.
I mean,
So,
this means only one Hamiltonian has the ground state. Normalized.
No, the other one will have a ground state, but it will have non-zero energy. I'm saying only zero energy.
But I mean, let's say ground state. For example, let's say harmony oscillator. Ground state does not have zero energy, but I can shift, right?
Yeah. But the point is, when you do shifting, since H1 and H2 both are related to each other by A dagger and A dagger, when you do shifting, you will shift the other one as well. So if you do shifting, you can make only one of them to have zero energy bound state. The other one will then shift to give a non-zero energy. You cannot shift both of them simultaneously.
So that's why I'm asking. I mean, is it? I mean, does this statement mean that the normalizable? I mean, only H1 or H2, whatever, will have the normalizable ground state?
Okay. If H1, no, I'm so ground state I define as the lowest energy state. So, so H1.
That I can always choose to be 0, right?
So I'm saying you cannot choose it to be 0 simultaneously for both H1 and H2.
That is fine. Yeah, that is the reason that is what I mean, what I'm trying to say, that your this proof actually tells you that the ground state is unique.
If you, I think you are thinking that both H1 and H2 are the same system. But if H1 and H2 are two different systems.
So Shubhankar da,
Yeah.
so if you think in terms of the big H, which Diksha wrote in
Yes.
component form as H1 and H2,
Then your statement
then
is
in the
correct.
big H thing, whatever you are saying is correct.
Right. I mean, I'm talking about the big H. So
Yes.
big
Yeah,
H.
then it is correct.
Yeah, I'm talking about the full system. When I'm taking both the Hamiltonians, so ground state appears only in one sector.
Yes.
Yes.
Yeah. The point is, in some of the cases, both H1 and H2 can be two different systems. So I was thinking in terms of H1 and H2, not in terms of big H when I was making the statement. But yes, in terms of big H, in terms of full supersymmetric system, the thing you are saying is correct.
Yeah.
Okay. So what we have shown till now, that if some phi n1 is some phi n2 is eigenstate of H2, then A dagger acting on phi n2 is eigenstate of H1. This of H1. This we have shown. And now this, since it's an eigenstate of H1, I should label it as some phi of 1, no? Some phi times 1, because I'm labeling all the eigenstates of H1 with the label 1. Now, the ground state thing I showed it just to tell you that this should be related to n plus 1th state. Why n plus 1th state? Because the 0th state, so phi 0, 1, since it has 0 energy, it did not have any corresponding pairing, so it had no pairing. So since it had no pairing, so phi 0, 1 should not be related to anything, but the phi 0 of 2 should be related to something because it had non-zero energy. So phi 0 of 2 should be related to phi of 1.
Diksha, actually, maybe you can draw a diagram that I think will help.
Okay, yeah, maybe. So this is, let me say this is the spectrum of H1 here. This is energy. This is the spectrum of H2. So here, so H1 had a 0 energy state, which I call it phi 0, 1. And then H2 had some state which you can call a ground state of H2, but it had non-zero energy, because I showed that if H1 had a 0 energy state, H2 cannot. So this will be phi 0 of 2. So the 0th energy state, the ground state of the second Hamiltonian. And now there is the first excited state of 1. So now this state should be paired to something. This is paired to the first excited state. So these two states have the same energy. Let me call it E1 of 1. And then phi 1 of 2 will be paired to phi 2 of 1. And so on. So except the 0 energy, all the other states are paired. And this is the pairing. So the 0th state of the Hamiltonian 2 is related to the first excited state of the Hamiltonian 1. So what I have, is it clear now? Okay. So what I have shown, that phi n plus 1, what I have shown is phi n of 2 can be related to A times phi n plus 1 of 1, So this phi 1 of 1 here, for example, can be written as A. Sorry, what I have written? Sorry. So phi 0 of 2. One second, I got confused with A and A dagger, what I had used. So if phi 2 is the state, then A dagger thing will be here. So this is A dagger. Okay, I have written opposite on my notes. So phi 0 of 2 should be A dagger, should be proportional to A dagger time phi 1 of 1. So I'm using some, let me normalize it. Okay. You can use some normalization, En plus 1 of 1. And then phi n plus 1 of 1 is related to A times phi of n of 2. So from the states of Hamiltonian H1, you apply A to get the states of Hamiltonian H2. I'm writing opposite, sorry. Yes, I'm writing it opposite. So what you will get, so the final thing is the n phi n plus 1 of 1 is square root of En. This is just a normalization. This I have chosen for convenience. Okay. This is just a normalization. A dagger of phi n of 2. So this is the point, no? I said it opposite. So if you apply A dagger on phi 2, you will get some state which is proportional to some state in the Hamiltonian 1. This is what I have written. So in the Hamiltonian 1, that state is n plus 1th state because it has to be related to the first excited state when you act A dagger on the nth state. And energy of n plus 1 state of the first one is related to nth energy state of the second one. Because the energy of these two states should be same. This is what I showed. So this state energy, I label it by n plus 1th energy of 1. This energy, I will label it as nth energy of 2. So these two energies are same. And phi n of 2 is related to En plus 1 of 1. A time. So if you apply A on the first Hamiltonian, you will get the state of the second Hamiltonian. Is it okay? Is it clear? I got confused in the notation a bit, but is it clearer now? Or should I repeat it?
So Diksha, I think the moment you do the example, it will become more clear actually.
Okay, yeah.
You're planning to do hydrogen atom, right?
Yeah.
Yeah. I think this is bit of formal, so that will be very clear. Then, yeah.
So okay, so you can try to verify this. So basically, what I'm trying to say, given the eigenstate of Hamiltonian H1, you can H1, you can apply A on that to get an eigenstate of Hamiltonian H2. This is what I showed also here. So given eigenstate of H1 phi n1, you can apply A on it to get eigenstate of H2. This is the last line which I have written. Applying A on the eigenstate of H1, you will get phi 2. Similarly, applying A dagger on H2, you will get a state of phi n1. And since the energies of these two states should be same, this I also showed that they are paired with the same energy. So the n plus 1th energy of the first Hamiltonian is same as the nth energy of this. Okay, we'll do an example. Maybe it will become more clear. So hence what we have shown, the spectra of H1 and H2 are related. So since the spectra of H1 and H2 are related, one can solve for a difficult Hamiltonian H1 by just solving for H2. Given H2 becomes simple. So for any generic system, you can define the corresponding supersymmetric Hamiltonian, but whether that
there's a question.
Yes.
Excuse me. Yeah. How did we prove that the nth state of 2 is related to the n plus 1th state of 1?
Okay, so this is basically from here. So since the zeroth state of 1 should not have pairing with anything, because zeroth state of 1 should has zero energy, because I already assumed that H1 is the one which has zero energy state.
Right.
So this will not have any pairing. Now
Right.
the zeroth state of 2, zeroth state meaning its energy is non-zero, but it's the lowest energy state.
Right.
So this lowest energy state should be paired to something, because what I showed, that if the energy is non-zero, given a state of 2, you can apply a dagger on that state, on this state, and this state
Right.
will be an eigenstate of 1.
Yes.
So since it cannot be the zeroth eigenstate because it has non-zero energy, it should be related to the first excited state of 1.
But
Because
some other eigenstate of 1 could have the same energy as the lowest state of 2, right?
no, but then the middle, if let's say phi 2 was related to this, but then phi 1 also should have some pairing, no? Because phi
Right.
1 is non-zero energy, because because this argument works for any non-zero energy state of any of these Hamiltonian. So where will the pairing of phi 1 go?
Okay. Fine.
Yeah, I think an implicit assumption is that for every energy, every Hamiltonian, there is a unique state.
Wait.
Yeah, then
Yeah,
it
if there
will
is
be.
degeneracy, if there is degeneracy, if there were two states here, then you don't know. So this could have gone to this one or this one. If there was a degeneracy, here, either this state could have been related to this one, or this state could have been related. Ananda, are you trying to say this?
Yes. That's what I was trying to say.
But
Yes, I
can
think
I-
that.
Yeah, I mean, usually when we had perturbation, okay. So you mean to say if I take higher dimensional systems,
Yes.
then I do not have this thing, this supersymmetric thing.
You have the supersymmetric thing, but you don't know which of the state you will relate it to. So even for the hydrogen atom, when I will show this happens. So when you reduce the system to the radial system only, so when you do the separation of variables and all, already when you reduce it to the radial thing, then you can do this procedure.
Yeah, actually, there is a small caveat only. And I agree with whatever Diksha said, but small caveat is that unless you have another extra symmetry. So usually, whenever we have degeneracy, there is an extra symmetry. And then if you have extra symmetry, then there are corresponding charges because of that extra symmetry. And whatever that charge doesn't change under supersymmetry. So then you can use that charge to identify the Bose-Fermi pairing.
For example, I get two-dimensional harmonic oscillator.
Yes. So then all the states will be some representation of SU3, and you can use the SU3 representation to do this pairing. Okay.
Nice.
Yeah, but if you add a generic perturbation, then SU3 will be broken. So that means the degeneracy will be lifted, and then it's a different story. Yeah. Okay. Yeah. Okay. Yes. Sorry. Yeah. Diksha, continue. Yeah.
Okay. And then you can just solve for another. And sometimes, as you will see in the hydrogen atom, so sometimes both H1 and H2 are related to same system. So in that case, you are basically relating different energy states of the same systems to each other. So then you can use that process iteratively to solve for the system. I will show this explicitly. So since I think this was a bit confusing in notation, it will be good exercise for you guys if you can try to do this. So if you take the superpotential W of X to be just X, define what is H1, then H2, and then and then try to find the eigenvalues. and relate eigenstates of both. You will see if you take this W of x, you will get harmonic oscillator.
So then both H1 and H2 are harmonic oscillator, right?
Yeah, both H1 and H2 are harmonic oscillator, but one has shifted energy.
Yeah, there is a +1 and
Other.
-1.
Yeah, one will have shifted energy, and and since this what from that what you will conclude that some n plus 1th energy level of the harmonic oscillator is related to nth energy level of the same harmonic oscillator, something like that, and then you can. So this will be a good example to do. Okay, only 7 minutes left. Let me just introduce the hydrogen atom thing, and then we will continue next time from there. Okay.
But Diksha, sorry, yeah, how much time you need for hydrogen? If it's 10 minutes more or something, then we can just finish it. It's not much of a big deal.
I don't know how much details I want to go in that because
Okay, let's see. Okay.
Okay. So the Hamiltonian of the hydrogen atom is basically h square by 2m del square minus e square by 4 pi epsilon naught r. So this is the Coulomb potential. So this is the Hamiltonian of the hydrogen atom. So I will put all the constants to 1. So I will take h cross equals to 2m is equals to 4 pi epsilon naught is equals to 1. I'm putting everything to 1. So now when you solve for the hydrogen atom wave function, what you usually write, you use separation of variables. So if this is the wave function, you write r. So it's a function of r, theta, and phi variables. It's a 3-dimensional. So this gradient is a 3D gradient. So you use separation of variables, and you define is as you define psi as u of r over r y l m of theta phi. These are the spherical harmonics. I hope everybody knows these things. So the spherical harmonics, and then the equation h of psi is equals to e of psi. If you use this, you will get the following radial equation. You will get del square by del r square. I am putting all the constants to 1. So u of r plus L into L plus 1 over r square u of r minus u of r over r. This is equals to e times u of r. So this term is h of psi times e of psi. So your Hamiltonian, I call it the Coulomb Hamiltonian at level L, because it depends on the L quantum number, is given by.
Yeah, I think you are comparing the S wave, right? There's an M term, right?
Yeah, no. So this m, this is m, no. This is spherical.
No, small m is that LM, the spherical harmonics LM, not the mass M.
Yeah. But the m, you're saying m appears in the gradient. I'm not writing that
Okay,
down.
this is gradient. I thought,
This is just the radial equation, no?
and M is there? Oh, wait, no. Okay, yeah, maybe go ahead. Maybe I'm missing something. I thought there's some M.
No, M doesn't appear.
M doesn't
M
appear.
doesn't appear in
Yeah,
the radial. It just appears in the ILMs.
L into L plus 1, right. Yeah, L equals to 0 is the S wave part. Yes, go ahead. Sorry.
This is the angular momentum part, yes.
Yes, fine. Go ahead.
So the del square by del r square. So this is the Hamiltonian plus L into L plus 1 over r square minus 1 by r. So this is your Coulomb Hamiltonian. Okay. Now let's take the superpotential to be following. W at L of r. So it's a function of r and it's labeled by L, no? Because at each L you will have a different Hamiltonian. let's take the superpotential of X to be, so WL of R is given by minus L plus 1 over R plus 1 by 2 L plus 1. Okay, and now we can define A L to be d by dr plus W of L, which is basically d by dr minus L plus 1 over R plus 1 over 2 L plus 1, and A dagger of L is minus d by dr plus W of L. Then you can do this exercise. Okay, so I'll ask you to check this. So what you will find that you can define the first Hamiltonian H1 at level L to be A dagger L AL, and this turns out to be minus d square by dr square plus L times L plus 1 over R square minus 1 over R plus 1 by 4 L plus 1 square. So this is basically the Coulomb potential at L. So HL of Coulomb plus you have an additional 1 over 4 L plus 1 square term. So this is HL of 1. Similarly, HL of 2 is given by, okay, I will write explicitly, dr square plus L plus 1 L plus 2 over R square minus 1 over R. So H of 2 was basically A dagger L. Please check this when you try to do the computation. L plus 1 square. So this is basically H Coulomb, but at level L plus 1. Notice the second term. So it's L plus 1 times this. So it's H Coulomb at L plus 1 plus 1 over 4 L plus 1 square. This is HL of 2. So this is HL of 2, this is HL of 1. So notice that now both the supersymmetric Hamiltonians get related to the same system, which is the Coulomb potential, but at different L. So hence we can use supersymmetry to relate the eigenfunctions. So we can use SUSY can relate eigenfunctions at level L to level L plus 1. Okay. You can also note that H1 and H2 are also related to each other. So H2 of L is same as H1, so H Coulomb L plus, sorry, H2 of L is H1 at L plus 1. So if I put, so I can substitute H Coulomb to be H1 at L plus 1 minus 1 by 4 L plus 2 whole square, no, here. So this will be minus 1 by 4 L plus 2 whole square plus 1, this term was 1 by 4 L plus 1 whole square. This thing basically was H Coulomb of L plus 1. You can check. So H1 and H2 themselves are related to each other. So Lth level of H2 is related to L plus 1th level of H1 plus some shift. Okay. So let's begin with, is it clear or I'm going too fast? Okay. So let's begin with the ground state. Ground state of H1 of L. I label that, I call it U, since it's ground state 0 at L, because it's corresponding to HL of 1. So even ground state is unique, so you do not even need to write this one, but I am writing it for the sake of convenience. So the ground state is basically H1 of L acting on this U01 is 0. This implies AL acting on this U0L of 1 is 0. So what you will get d by dr. So in this case, I already knew. I don't know how people knew what was the superpotential initially. So since I already knew the superpotential, I'll use the superpotential to construct the ground state instead of doing the other way around. Plus 1 by 2 L plus 1. This is the A acting on U0 L of 1 is 0. So this is the ordinary differential equation. You can solve it and you can find that U0 L of R is R.
How did you find the superpotential?
So this superpotential, I don't know how people found in general, whether it was a guesswork or people found it like from the ground state. But since the way I am explaining it, I'm just saying that I know I took this superpotential. I didn't know which system it would correspond to, and I found that it corresponded to the hydrogen atom. And then using the superpotential, I'm computing the ground state. But I think in general, it's done the other way around. Or if you can guess the superpotential, then it's another thing.
Okay, I mean you take W of that form so that you get both L into, I mean that that Coulomb term and the other term, right?
Yeah. And the yes.
Centrifugal potential or whatever it is called, yeah.
Yes, so you take W to be of this form so that you can get both the angular momentum term and the Coulomb term.
Right. W prime will give you 1 over R square and the other term will give you 1.
Yes.
I see.
Yes. So this is the ground state that you will find. You can also like just solve this, check as a homework if you want to check. Just solve this differential equation. Okay.
I mean, here the beauty is that you can so easily write the explicit expression of the wave function, which is usually so difficult in the ordinary way we do.
Yeah, you have to do this radial expansion, then series solution.
Yeah, because in earlier, if you were solving directly from the radial equation, this was a second order differential equation in R. But now using supersymmetry, I have reduced the second order differential equation to a first order differential equation, and it's in general easy to solve first order differential equations. So supersymmetry. So this is so if people know more about supersymmetry, this is basically the BPS condition in a sense. So supersymmetry reduces your second order differential equations to first order differential equations. So that's why it's easier to solve. Okay. Okay.
In this case, it's kind of, you are lucky that you know this superpotential, but in general, it may not be easy to find a superpotential which will fit my potential.
Yes, that's true.
Yeah.
So the difficult part in this thing is to find the corresponding superpotential. Once you have found it, then the problems become easy. So the only tricky part is to find the superpotential.
I mean, is it true that if I have any 1 over R to the power n potential, is it always true that I can find the superpotential in this way?
I don't know. I haven't tried to write generally because if I had but it will, if you had 1 over R power n and R power n plus 1, both terms with opposite sign, then you can see, because the differentiation of one term will give you the other. And in the superpotential, you have a W prime term.
Your voice is, I do not know whether it's a problem from my side or not. Yeah, your voice
okay. Sorry. Okay. Can you hear me now properly?
Yeah, fine, yeah.
So I am saying if you have a term like in the Hamiltonian, if you have 1 by R power n and R power n plus 1 term also, then in the potential, when I wrote the potential in terms of the superpotential, there is a derivative of superpotential that will occur. So if the potential, you needed both these terms, then it's easier to find a superpotential because the derivative will give you the other term. But I don't know if you can do it in general. Like there are these notes. Okay, I don't have the link of them right now. In the next lecture I will give, they have done a lot of examples of this type of cases. So they have done the harmonic oscillator, hydrogen atom, and some 2-3 more examples also.
Yeah, that is exactly what I was trying to say. I mean, if I take a 3-dimensional harmonic oscillator,
Yes.
where again the potential is, I will get this L into L plus 1 by R square term,
Yes.
and then I have a R square potential,
Mm,
R potential, right? Sorry, R
yes.
square potential.
Yeah.
So can I mean, do it? Can I construct the superpotential for 3-dimensional harmonic oscillator also?
I don't know. I haven't tried to do it, so I don't know.
So I mean, so I have a term like 1 over R square and plus R square. So I mean, A by R square plus B R square. So can I
Yeah.
construct superpotential?
I don't know. I can try
Yeah,
to.
so Shubhankar, as far as I know, you can construct it with up to a shift.
Yeah, shift is fine, right? I mean, constant shift in the Hamiltonian is not a problem.
Okay. Yeah, but I don't know. Okay, even for R, 1 by R square plus R
I
square
mean,
type
yeah,
of.
or no, in this case also you find the potential, you find the Coulomb potential up to a shift, right?
Yes, yes.
In this case also there is a shift.
Yes. So
Shift or
so yeah, as far as I understand, Shubhankar, that there is some connection between every super integrable classical system and a supersymmetric system. Apparently, every super integrable system, I'm just saying some technical words actually at this point. In classical mechanics, apparently all such systems can be embedded in a supersymmetric system. I don't know a proof, but apparently this is a result actually.
super integrable mean you mean exactly solvable?
Super integrable also means exactly solvable. Super integrable means that the number of conserved quantity is so if you have a system which space is 2n dimensional, then if the number of conserved quantity is more than n, then you call such a system super integrable, and apparently those systems can be embedded into supersymmetric systems.
I see.
Okay. Okay, I think should I complete this hydrogen atom thing?
Yeah, it depends on the organizers. It's already 5:10.
Or we can do it the next time so that people have some time to digest this.
I think this is a good point to stop. You have
Yeah,
found.
besides the grounded, next time we'll find the excited state. It will just take
Yeah.
10-15 minutes and then we can go on to next topic.
Yeah, I also agree because this part is though obvious, but it needs some amount of computing. So it's probably good time to people to stop and go back and then
Yeah.
on Monday maybe.
Okay. Yeah. So, okay.
Questions?
Hi, I had a question. Actually, my connection was bad, so probably I missed this. Is there any assumption on the nature of the superpotential W of X? By that I mean, are you assuming it is parity invariant or it's an odd function?
Okay.
I mean, the reason why I am asking this is that because you gave V of X to be a particular formula, it was derivative plus something quadratic. Because
Yes.
the nature of W of X is going to ensure the nature of V of X, and that better be something which is bound, which should make sure that my Hamiltonian is bounded, or else I will not have a ground state, right? That's
Yes.
what I
So,
was.
so if you have, so yesterday I introduced an operator minus 1 power f. So if you
Right.
have that operator as the symmetry of your system, so that operator usually commutes with the supercharge. In that case, your superpotential is odd function of x.
Always.
Is it true? Or another, am I confusing the target space and that again?
No,
Because
I think let's put in this way that if your potential is parity invariant, then super potential should have a definite parity, either plus or minus. It cannot be mixture of something. If it was your question. Okay, and in general,
Right.
if your theory has some particular symmetry, then superpotential is, if it's a continuous symmetry, then superpotential has to obey that symmetry and certain things. Okay.
Yeah.
Yeah.
Okay.
So that's I mean, I'm not sure that was your question or not. Was that your
I
question?
mean, it was the other way around because we are assuming something about superpotential and then we are writing down the full Hamiltonian. So I need to start with an assumption about superpotential, right? Instead
No,
of,
but
I mean,
point is
W
that
of
if you know the full Hamiltonian, you know its symmetries, right? Correct?
right.
And that at least
right.
gives some heads up for you to what are the superpotentials you can, I mean, you can start your application
Okay.
process.
I see. Okay. I see what. Yeah.
Okay. Yeah. Okay.
Yeah.
Yeah.
Thank you.
Any other question? Okay, so let me just say one more thing. So Mukta is uploading all this thing in a particular Google Drive with Diksha's handwritten notes and all the videos. So if any of you are not getting it, either email me or Mukta or Gurmeet, and we will give you the link. Okay, and
Yes, I'll send the link today.
yeah. So and next one, should we do Monday?
Yeah. For me, Monday is fine.
Now, Mitadi?
Yes.